Hello everyone. As we all know that modern cryptography has expanded to elaborated functionalities and complexities where proofs are not just complex and complicated, but they are also difficult to check. But there are tools that provide us confidence in the security proofs by checking and reading the definitions and theorem statements without requiring anyone to read the whole proofs. It's just because the tools ensure the correctness of the reasoning steps. Now let's look at something that hasn't been formalized in the tool before, and that's the formalization of the two signature schemes, that is ADL and Chevalier-Mens, which are based on discrete logarithm problem. We reformulated both signature schemes pen and paper proofs and developed them in a tool called Easycrypt. So firstly, I will start with the ADL scheme with the background knowledge, security proof, and then the formalization. So basically this paper was presented by Go and Jaworski, where they showed that the ADL signature scheme, whose security is tightly related to the computational Diffie-Hellman problem. The scheme is parameterized by two random oracles H and G. So in this figure we define the ADL. In signing, to sign a message M, the signer hashes the message M with a random R is sampled here before, to obtain H and compute Z is equal to H to the secret key. In the dashed box here, it produces a non-interactive zero-knowledge proof of discrete logarithm equality with a basis a message-dependent hash, generator, and discrete logarithm. In verification, it just recomputes the message-dependent hash and verifies the non-interactive zero-knowledge proof. We consider the notion of existential forgery under adaptive chosen message attack, UFCMA, in which the adversary has the public key and access to both random oracles and to a signing oracle that signs messages of the adversary's choice and produce a valid signature on a fresh message. Here, we have an experiment of UFCMA and the advantage, and it states that the advantage of winning the game is the probability of returning a valid forged signature. And here we have the experiment of computational Diffie-Hellman problem and the advantage of the adversary solving the CDH problem. So here we have the advantage of ADL signature, which is to prove the tight security reduction from the hardness of the computational Diffie-Hellman problem in the cycle group to the UFCMA. So we will be proving that any adversary that breaks the UFCMA security of the scheme we consider can be used to solve the CDH problem with overwhelming probability. So our security proofs are concrete, and reduction from the CDH is displayed in this figure here. In this figure, the adversary has UFCMA forger as a black box, which internally simulates oracles H and G. The key insight in the reduction is to embed the CDH challenge across the signing scheme and its random oracles, then simulates the signing oracle, and then finally uses the forger queries to the simulated oracles to solve the CDH challenge. In oracle H, we embed the CDH challenge. In signing, we simulate the non-interactive zero-knowledge proof, and then in reduction itself we extract the solution from the random oracle. And then we prove that the probability that this reduction solves its CDH instance is in fact closely related to the probability that the forger F finds a valid forgery. We do this in 4 steps, which are actually common between the two proofs we formalize, and which we believe form a proof schema that will apply more broadly to a number of signature schemes. Formal analysis can be carried out through machine check proofs. Machine check proofs are an emerging approach giving us independent verifiable proofs of security, and proofs are verified with SMT solvers and automated theorem provers. As I mentioned earlier, that security statements are proved in Easycrypt. Easycrypt is an interactive proof assistant designed to construct machine-checked game-based cryptographic proofs in the computational model, where games and definitions are modeled as a probabilistic procedures. We formalized these definitions in Easycrypt exactly as displayed them, and also formalized proof as described now. Here we have our intermediate games and the shim. To make the formal proof slightly less tedious, we factor out everything that does not change in the intermediate proof steps into a shim that's parameterized by some oracles. This means we can only focus on reasoning about the bits of the code that change between two games, and the rest of the proof comes for free. For example, when looking at the transition between game 0 and game 1, you can see that we only change oracle H and sign, and it becomes obvious that the behavior of the game can only differ if the behavior of the signing oracle is different between the two games. This only occurs if the adversary somehow guesses the value of R, which occurs with a low probability. The first game, game 0, is equivalent to UFCMA security of ADL, and that the final game, game 2, is equivalent to the CDH experiment on the reduction with some bits added at the end. Another important aspect, which is the probabilistic relational or logic judgment, where we used it in the third step. And Easycrypt features a specialized program logic to reason about probabilistic equivalences between programs in the form of PRHL judgment. So a single PRHL judgment can be used to prove for equivalences up to a failure event, which is defined over both distributions here. For instance, we will be proving that these two games are equivalent unless this failure event bet G happens. So, with a single equivalence proof, we counter the failure event bet G, which happens with the same probability in both games, and that a forger that wins against the game 2, game second, also wins against the third game unless it runs against the third game, which triggers the failure event bet G. Now we show in this step the reduction. Here we prove that the forger's success probability has one of the two cases. Either it solves the CDH instance or exploited the unsoundness in the proof of discrete logarithm equality, which happens with a low probability. So the second scheme that we formalized is the Chevalier-Mann scheme, but the resulting signatures are smaller than the ideal signatures. The main difference in the CM scheme is that the message is now not included in the random oracle query to H, which served as the second base for the proof of discrete logarithm equality. Instead, the message is included as input to the challenge generating random oracle query in a way similar to the standard Schnorr signatures. So, for CM's formalization, we replay our ideal proof over the scheme, and we show they carry over similar objects as we sought out similarities and attempted to factor them out, except in the reduction step of the CM scheme, which has an additional case to consider, where we reuse the same shim with a very minor tweaks and show that proof differs only in the probability bounding and in the reduction step. For more details, kindly look at our paper. In the end, I would like to say that our formalization effort allows us to identify proof principles that we believe the proof pattern extracted in this way of our formalization could be adopted to other existing or new constructions to obtain new proofs of tight security. Thank you.